Alright, let's take a look at this system we've seen before, but now we're going to have a rough surface between mass 2 and the tabletop, or whatever we call this. We're going to apply a force to mass 2, and that's going to cause the motion to be in the positive x direction like this. It's M1 will go up, and M2 will go to the right. We're given that the masses are M1 and M2. We are given a force, the magnitude is F, and it's at some angle theta. It's going to move to the right and has coefficient of friction mu. They want us to find the acceleration. Typically concerned with accelerations. Okay, well, let's start by doing free body diagrams. Free body diagram on M1. Well, if here's M1, we're going to have M1G going down and some tension going up. Now I beg of you, do not say that tension is equal to mass times gravity. That is absolutely wrong. Let's go ahead and sum the forces on this, and I'll show you what it's equal to. I'm going to get rid of the y subscript on the acceleration just because since they're connected by an inextensible cord, the accelerations are going to be equal. The directions are just going to change due to the pulley. So the acceleration of 1 is going to equal to the acceleration of 2, or at least the magnitudes. But if I sum these forces in the y direction on mass 1, I get tension minus M1G is equal to M1A. So it indeed does not equal mg. It equals m1 times the acceleration plus m1 times gravity. Alright, let's look at mass 2. On mass 2. Okay, mass 2, we have a force that's being applied at some angle theta. Let's go ahead and break that up into x and y components. We have some f cosine theta and some f sine theta. We have a tension going to the back, right, going this way. We also have mg going down, m2g, and some normal force going up. Now they told us it's also a rough surface, so we have some frictional force going back also. So let's sum all the forces in the x and y direction on this. So I sum the forces in the x, I'm going to get this positive f cosine theta, and then a negative tension, and a negative force of friction. That'll equal to the mass times the acceleration. Is that everything? I think so. Alright, so this is equation 1, this is equation 2. I'm going to be doing some algebra, or I'm going to probably leave it up to you actually. If I sum the forces in the y direction, then I get a normal force going up, m2g going down, but then we also have this component of the force going up, f sine theta. And that equals the mass times the acceleration in the perpendicular direction, but it doesn't accelerate in that direction, so we can say it's equal to 0. I'm going to go ahead and do a couple steps of algebra for you. We could basically solve it from here. But we know that the frictional force is equal to mu times the normal force. So I'm going to take what I call equation number 3, and I'm going to solve it for the normal force. It's going to be equal to a positive m2g and a minus f sine theta. Okay, if I take this frictional force is equal to mu k. They give us mu k. And then substitute this relationship I just came up with, m2g minus f sine theta. That is our frictional force. And let's call this equation number 4. If we take equation number 4 and this equation from our tension, and put them all back into equation 2. So in this case it would be equation 4 into equation 1 into equation 2. Any which way. What we're going to end up with is a f cosine theta. It's this right there. Minus, and then after substituting the relationship for the tension, we get a mu k. It's basically this right here, m2g minus f sine theta. And then we also have the m1 times the acceleration plus the acceleration due to gravity. That's all equal to m2 times the acceleration. Now you can solve this all for the acceleration, dividing by m, but it simplifies a little bit more. And I want you to see if you can get this, because not only will you have to do this, but you're going to have to plug in a number and make sure you get the right value. So it's not a simple problem and doesn't leave much room for error. Make sure you can do this. It should simplify to something like this. And you can throw some numbers in there if you want. Check it out. That's our acceleration. That's what happens when we have a bunch of forces, right? We end up with more equations. We have to look at both directions, even if there's not motion in that direction. We introduced friction now, so this normal force really matters, right? Work as many problems as you need to understand this. But what did we do? We had two masses. That made me do two free body diagrams. So that's my step right there. I saw two masses, we need to do two free body diagrams. I labeled all the forces, and then from each one I summed the forces. We could have summed the hanging mass in the x direction, but there's no acceleration in the x direction, and there are 0 forces in the x direction, so we just get 0 is equal to 0. The only thing we got information from was summing the forces in the y direction on mass 1. But we had all kinds of crazy forces over here on the mass 2. We had to break up one into components, and we had multiple in each direction. I had to sum the forces in the x direction. I had to sum the forces in the y direction. We have to realize that this tension is the same as this tension. We needed to remember the formula for friction. All of those relationships put together gave us this sweet-ass solution. So check it out. Make sure you can get that all by yourself.